Bismillahirrahmanirrahim. The topic we will discuss today is properties of advanced material, under which we will discuss about dielectric properties. First of all, we see its key points, key concept. For example, key concept, dielectric properties of advanced material, in which we will discuss about um, advanced materials, nanoparticles, dielectric nanoparticles, and types of dielectric materials. There are two types of dielectric materials, which are paraelectricity, ferroelectricity, and their applications of dielectric materials, dielectric particles of advanced material. In the next, we will discuss about advanced material. First of all, we define advanced material. An advanced material can be said to be a material which has engineered properties created through the development of specialized process and synthesized technology. And we will relate the dielectric properties of advanced material. About it, that produce a petition to refer to all materials that represent advances over the traditional material that have been used for 100 or even 1000 of years. So from this perspective, advanced materials, we can say that it refers to all new materials and modifications to the existing material to obtain superior performance in one or more characteristics that are critical for the application under consideration. By modifying the previous existing material, we can make advanced material that have outstanding properties, and we can modify according to our requirements. So advanced materials can exhibit or can show completely different properties. So these advanced material typically have properties that are superior to and perform conventional material in their applications. So the development of advanced material, development of advanced material is designed of completely a new product. So advanced material are more, it could be modified according to our requirements. So in case of advanced material, we talk about nanoparticles and nanomaterials and nanoparticles. Nanoparticles are particles between 1 and 100 nanometer in size. In technology, nanotechnology, a particle is defined as a small object that behave as a whole unit with respect to properties. You know that nanomaterials are materials that have a size in the range of 1 to 100 nanometer, at least one dimension in the range of 1 to 100 nanomaterial, and below this way their properties can completely change. When we talk about advanced material, that the latest material that are mostly being used as advanced material are nanoparticles and nanomaterials, and nanoparticles and that are mostly being used as advanced material or nanomaterial, and that are under consideration, and that are mostly most widely used and studied over nano materials. The nanomaterial and nanoparticle, that nanoparticle which have size in the range of 1 to 100 nanometer, and a particle of any shape with dimensions in the 1x 10 raised minus 9 and 1x 10 raised minus 7 range are called nano particles are nanomaterials. In the next we um, we will discuss about dielectric nanomaterials. Why dielectric nanomaterials? Mm, we consider them for dielectric properties. So what kind of variations occur in the dielectric properties? If we consider that nanostructure and third of bulk material are microstructure, what kind of it so we need to discuss dielectric nanomaterial, or why does one want to look at the applications of dielectric nanoparticles and of articles, why they do not want to choose the micro size or bulk materials, what is the importance of that nanomaterials. Mm, the most important thing is that true electronic devices like computers or images processing devices, you can see in digital cameras, it is digital cameras, and everything has integrated circuits or chips which have many dielectric involved in it. So nano of these dielectric uh, uh, what is multi-layer ceramic capacitor? What is MLCC? MLCC mean multi-layer ceramic capacitor. That is the abbreviation of MLCC. The main material it is used as multi-layer ceramic capacitor is a barium titanate. So this barium titanate act as a capacitor, and it is involved in the fabrication of chip. It is applied in early devices. So this utilizing in these devices. So the size of chip are the feature size as we see is about 12 micron. It was 12 micron in 1990s. Below 12 micron, and people could not make a chip in 1990s, but with the advancement of technology and with the advancement of knowledge, um, the progress of working on advanced material, today the size of chip has been reduced to nanometer range. In 1990 it was about 12 micron size, but now the people can research, you and scientists can reduce the size up to nanometer range. This decrease in size has the advantage that is that can that you can put many chip in the same area. So the total amount of chip of total amount of number of chips, and that will be added on the memory of the devices, or whatever the property it is being applied. If we reduce the size of that chip, we can put many chip in one place. We can increase the memory of that device by reducing the size. Therefore, as we want to add a number of chip on a particular in a package system in electronic devices, so if we reduce the feature size, and if you reduce it up to nanometer range, then we will be able to putting more number of chip on a single device. Here a question arises that how you can reduce the size of chip. This is very important. So as we are talking about multi-layer ceramic capacitor that is being used in these chip, so the thickness of these layers should be reduced. Multi-layer ceramic capacitor mean that several layer of these ceramic capacitors are involved. If each layer is made up of barium titanate material, and if we use nanoparticle instead of micron size particle, then we will be able to put many such layers in one chip. Therefore typical sizes will go 100 will be required for such multi-layer ceramic capacitor or for such multi-layer ceramic applications. Now we will discuss about dielectric nanoparticles. Dielectric nanoparticles are very important because you can pack these nanoparticles in a very dense manner, and they will still have high surface area because the particle size is very small. And if you can reduce this dielectric oxides nanoparticles to the size of nanomaterials, then you can think of making dielectric layers with less thickness, and that will be very advantageous by making the final side of the chip is very small. The other property which is important, why we should go for nanoparticles of these dielectric material, if these nanoparticles can be dispersed in a different matrix media. You can have a polymer, you can have metals, put it many materials could be used as starting material. And that could be matrix are dispersed with dielectric nanoparticles. They can finally dispersed in a different media. Therefore we can take different starting material, and we can mix up with a different dielectric nanoparticles. So that is one important. And we can make our composite like polymer dielectric composite, and then because of the polymer it will have a flexibility. And then you can meet what are flexible, what are hard flexible, the electric field. So dielectric nanoparticle are embedded within these polymer films. Now if a polymer with this dielectric nanoparticle, then you can prepare these flexible electronic films. These are known as embedded dielectric films, because in this dielectric nanoparticles are embedded with these polymer films, and these are flexible. So such flexible films are important in flexible electronic devices, especially in cell phones, in laptops, and another applications. So this is also very important for the other future applications. Another important of it for using nanoparticle is our dielectric measurements. There is a strong materials, there is a strong dependence of DC voltage for bulk material. You have to apply DC voltage, whereas if you reduce the size of nanoparticles, you can see that 50 volts applied voltage will be with 60 to 80% loss in capacitance. So this dependence on the DC wires can be reduced by using nanoparticles. So less voltage can be used for nanoparticles. Another factor that is important is lower loss of nanoparticles, which are dielectric nanoparticles. And lower loss means lesser dissipation factor, and dielectric nanoparticles will have a much lower loss energy. It has a less dissipation factor as compared to micron sized dielectric material, large bulk size dielectric material. Therefore all these properties are make an important for the person for one of understand and fabricate devices that are built up of dielectric nanoparticles rather than micron size particles. The we can these multi-layer ceramic capacitor material, then we can bring MLCC, bring down the thickness. It means we can reduce the thickness of this layer. Hence these thin layers dielectric layer will allow you to make smaller devices. So if we reduce the size, we can make smaller devices that are smaller in size, but ability or their properties are much better than the bigger one. So we can say that it can be reduce the size of dielectric material. We can prepare small devices or small size devices which can increase the properties. The other things is that we prepare flexible material. If flexible material embed them with a flexible polymer, and two other important point are that um, nanoparticles you can in nanoparticles you can overcome this strong dependence on DC voltage, and you can also lower the energy loss of dissipation factor by using nanoparticle mm, as paired as compared to conventional or bulk particles. So there are different examples of dielectric materials in which many peoples are working. The best examples is strontium titanate, um, that have been prepared in a micron or a half of micron size, and people are further research are trying to reduce the size to nanoparticle range, and the pin size is shorter, and the size is a smaller one dimension in nanoparticles, nanomaterials. Nanoparticles and nanomaterials, then the properties are further enhanced. So if we look at the in the next slide, if we look at the mixture of micron size and cannot sized particles, we can make a composite of nano and micro size particle, as we discussed previously, that we can embed nanoparticles with the polymer matrix. So when we mix this micron size and nano size particle, we can see that when we are adding micron and nano size particle of the same material. For example, here we take the example of barium titanium oxide, the particle in micron size, and also you can take the same material nano sized particle. Then you will mix these particles, and in this diagram you can see it show that what this material particle will do these small particle can join the large particle, because the small particle has lower because the small particle has lower material particle, it matters first, so it will have bonding these larger particles. So when you heat this smaller part melt first and it's centered. So we can get in this scheme we can get in this scheme in this kind of tens of nano and micro size particle, which are highly compacted. So in the figure you can see in the schematic diagram, you can see that these micron structure of nanoparticles and nanoparticles. mm, you can see in this schematic diagram, you can see that these microstructures of nanoparticles and the micron size particle, these aspects have been centered, um, centered, then they combine together and they form a structure like this. Mm, they form a structure like this. These are nanomicron size particles. So here is the figure. You can see on the left side scanning electron micrograph for barium titanate, and the right side is scanning electron schematic image for nanomicro micron composite of barium titanate, where you mixed these bulk and nanomaterial together, and here you can see the species which are due to the first melting of nanomaterial, and then they combine and the former grains, and in this and this is only 1% of barium titanate has been added, and this kind of very compact that mm, that compact grains which show signs of melted. It is due to dielectric property, and this is one weight percent of nanobarium titanate that has been added to bulk materials. So 99% is the micron size particle, mm, and this is one way person is vary the properties. So epsilon here is the dielectric constant, and when you brought it as a function of variation of the weight percent of nanoparticles, so you can add 1%, 2%, and 5%, like that is shown here for 30%, and we can see that you can see that for smaller region, small region, where addition of nanoparticle is around 1 or 2 or 3 weight percent, and that electric constant epsilon has shown an increase, and the dielectric loss, which is shown as a square, which is T is the dielectric loss, is plotted on the disk, and also shown increase in the body. So there are some changes when you add nanoparticles, the dielectric macron particles, and this is main due to the addition of nanoparticles that changes the phases of the micron nanoparticle, and the hence properties, and hence properties are changed. So in the next we will discuss about ferroelectricity. Ferroelectricity is property of certain material that have a spontaneous electric polarization that can be reversed by the applications of an um, external electric field. So all ferroelectric with the additional property, their natural electric polarization is reversible. So if this polarization is reversible material over ferroelectricity or other candidated, that property is known as the ferroelectricity. And the term is used in analogy to ferromagnet. So in ferromagnet, what happens in which mixed material show a permanent magnetic movement. Does the prefix ferro means iron was used to describe the property, despite the fact that most electric magnet do not contain iron, but the property is that case they have a permanent magnet moment, or they have permanent polarization, then we can say that material is a ferromagnet on that um, uh, on that material depend on the iron. Next we will discuss about paraelectricity. Paraelectricity is the ability of many materials, especially ceramic, to become polarization under an applied electric field. And so this happens even if there is no um, uh, permanent electronic tripods, as happens in ferroelectricity, and that exist in the material. And the removal of field reverse is in the polarization is that material returning to zero. So mechanism in that case, in the case of paraelectricity behaviors, distortion of individual or displacement of electron could form the nucleus. And and the polarization of molecules combine ions are defect. So this paraelectricity can be happens occurs in cluster phases, where electric dipoles are mostly unlined, and thus they have a potential to unline in an external electric field. So example of paraelectricity electric magnet of a high dielectric constant is strontium titanate. In the next we will discuss about its applications. Mm, uh, Applications of dielectric, these are mostly used in capacitor. So commercially manufactured to capacitors generally choose a solid of dielectric material with a high permittivity. The intervening medium between the two positive and negative charges that are scroved on capacitors. So we can say that this material as a capacitor dielectric alpha that is used in capacitors. Another use of dielectric material is barium strontium titanate thin films from 2002 to 2004. Army Research Laboratory conduct research on thin films technology. Barium strontium titanate is a ferroelectric titanate factor since was ready for the fabrications of since ferroelectric thin films studied for the fabrications of radio frequency and microwave components such as voltage control oscillators, tunable factors, filters, and phases shifters. Mineral oil is used inside electrical transformers as a fluid electric and to exist in cooling. This research was a part of effect to provide the army with the highly tunable microwaves, composite materials, broadband electric field, and tunable devices, so which can operated at constantly or consistently in extreme temperatures. So this work improved the modifications of bulk medium strontium titanate, which is a thin film that enables the micro modifications of electric components. 2004, the research paper, that was army research paper, they explained that how small concentration of acceptors droplet can dramatically modify the properties of ferroelectric magnets, such as barium strontium titanate. So when we modify and we dope this material, we can change the property of dielectric properties of that material. We can convert the para electric material to ferro, and we can convert the ferroelectric material to paraelectric material. In this case, researcher dope beans as strontium titanate thin films with magnesium, and analyze the microstructure surface morphology, and since substitute some positional quality of the results. Magnesium dope these variations function tightening in show to improve dielectric properties, and no current leakage, and good durability for this material, which show that potential for the use in microwave tunable devices. And therefore our dielectric material can be solid, that they can be liquid. Our dielectric material can be solid, they can be liquid or gases, and in addition to these, we can say that um, high vacuum high vacuum can also be useful, and it could be useful as a dielectric, even though it is relative dielectric constant is only one. Solid dielectric are generally most commonly used dielectric that are used in electrical engineering. Many solids are very good insulators. Some example included include for solid insulators are dielectric are porcelain and glass, and most plastic and work as a dielectric. Air, nitrogen, and sulfur hexafluoride are these most commonly used gases. Dielectric these commonly used gases in dielectrics. So in case of liquid, the material oil is used inside electrical transformer as a fluid dielectric, and it is used to exist in cooling. So dielectric filled with high dielectric constants, such as electrical grade castor oil, olefins used in high voltage and capacitor to increase capacitance. And some ionic crystals and polymer dielectric exhibit ferroelectric effects. And ferroelectric materials have very high dielectric constant, making them quite useful for capacitors. This is all about today topics.